In today's lesson, we are going to continue on looking at different ways to kind of order things and kind of branching off of the last lesson where we looked at permutations with identical or non-ordered elements. And we're going to be looking at what we call combinations. So just as a warm-up, so Lotto 649 is a Canadian lottery that has 49 numbers and is based on selecting 6 of those without replacing them each time. So a common question with the lottery is, does order matter? And we want to calculate or think about calculating the number of ways to draw the numbers if order did matter. So in this type of question, if order did matter, we would be looking at something like permutations, which we've talked about in the previous lessons. So you could think about, well, I have 6 options or 6 positions, 49 numbers for the first one, then 48, 47, 46, 45, 44. Or you could do 49P6. Now, what I want you to think about is, would this, or if you looked at this question where order didn't matter, so if order did not matter, would you have more or less ways to come up with 6 different numbers? Right? Or would this change if order didn't matter? And consider the size of the number that you calculated and the probability of getting the one order that would win. So think about that for a second. Right, if you have to pause the video, you can, but just kind of think. We have we know how to figure it out if order did matter. Would you have more or less ways if order didn't matter? And then think about the probability or the size of the number you calculated getting the one order to win. So if you were to do 49P6, you would get a value that works out to 1.006 times 10 to the power of 10. So an incredibly large number, right? Looking at roughly 10 billion, I believe 10 billion different orders of the numbers. And if you think about that, in order to win the lottery, you would have to sell at least 10 billion tickets. And if you sell at least 10 billion tickets, then you know one of them is going to win. Right? And it makes sense from a consumer perspective as well. You want to be able to win, you want to have a chance. If you say you have a 1 in 10 billion chance of winning, you're probably not going to buy a lottery ticket, right? So thinking about that, if order didn't matter, we should have less ways. If we had more ways, then it wouldn't make sense, because again, it'd be too many options. So if order doesn't matter, it means there are less ways in the end. So we're going to be looking at situations where when we're selecting objects or selecting elements, order does not matter. So that's going to be what we're looking at today. And when order does not matter, that basically is being referred to as combinations. So a combination is a way of choosing or grouping a set of R objects from a larger set of N objects. And it's very similar to a permutation with one major difference, and that difference is that order does not matter in a combination. So it does not matter what position we choose them in. The idea is that we're just choosing those objects. And the notation is very similar to permutations with some added differences. So we have C and R. N we've already referred to as basically the total number of objects. R is the number of objects chosen. And in a factorial notation, it works out to n factorial divided by n minus r factorial times r factorial. So basically what we're doing, it's almost like the permutation formula. Right? This section here is the permutation formula, but we're dividing it by an extra r factorial. So we're basically dividing it, or we're trying to cancel out the different ways that we could order the elements. Similar to, again, what we looked at with non-ordered elements or the identical elements in the previous lessons. The combinations can also be written as NCR or in kind of a matrix NR. It's not a fraction, so please be careful of that, but different ways that we could represent it. Again, N is telling us the total number of objects, and R is telling us how many objects we are choosing. So what we're going to do is just kind of try to differentiate between a permutation and a combination. And what we're going to do is just complete the calculation, determine if it's a permutation or a combination, and then if it, depending on what it is, we're going to rewrite the situation so that it uses the other operation. So A, we have decided, we have to decide how many ways to put 15 players into 5 different starting positions in a sport. So in this one, because we are putting them into 5 different starting positions, so you could say, for example, a lineup in baseball, right, or maybe a shootout in hockey or soccer, penalty kicks, something like that. In this case, order would matter because we are putting them into specific positions. So in this case, it would be a permutation. And in that case, we would have 15 objects, and we are picking or ordering or arranging 5 of them. So 15p5. And we get 360,360 different starting positions. In terms of rewriting the situation so that it uses combinations, or in other words, order doesn't matter, it could be something of an example of, let's say, how many different teams of 5 can you choose from 15 say tryouts. Tryouts are rookies or players. So the idea in this case is that I don't care, or it doesn't matter who gets picked first. The idea is that you're picking 5 people or choosing 5 people for a team. So how many different teams of 5 can you choose from 15 tryouts or 15 players? Again, the order doesn't matter. It's just the idea is how many people or how many different ways or different teams could you have. It doesn't matter who's picked first because they're all going to be on the same team. For B, out of 10 pairs of socks, you have to decide which 3 pairs you want to pack in your suitcase for the weekend. So in this case, we have 10 total objects or 10 pairs of socks, and we want to decide which 3 pairs you want to pack. So in this case, you have to think about, does it matter what order I pick the socks in? Or is the question only asking which pairs am I going to pick? Or which pairs am I going to choose? So in this case, this is going to be a combination. Because order does not matter. It doesn't matter. The question is not asking how many ways can I order 3 pairs of socks out of 10. It's just asking how many different different combinations of 3 pairs could I pick, essentially. So in this case, we have 10C3 which works out to 120 different combinations of 3 pairs. So I'd have 120 different combinations of socks that I could pack for the weekend. If I wanted to rewrite this sentence to be a permutation, I could do it as something along the lines of how many ways could you arrange 3 pairs of socks in your dresser or suitcase, or if you want to keep the same theme. But the idea here is that we are going to arrange them. So in this case, the order does matter. So when we're arranging things, order does matter. For C, I'm going to let you try on your own. Again, read through the question, think about, is order important in this scenario or is it not? Come up with the calculation to figure out how many different ways the scenario could be done, and then try to rewrite the scenario or come up with a different question that uses the other calculation. So for C, this one was a little bit easier, but we should have realized that this is a combination. And the key thing is that it says out of the 30 different songs, we need to decide how many different playlists of 10 songs could we make if order does not matter. So if it ever says that order does not matter, that's a clear giveaway that it's a combination. In this case, we found that there was 30,045,015 different combinations of 10 songs. And if you wanted to rewrite it to involve permutations, you could choose to say how many different top 10 lists could you come up with from 30 different songs. So in this case, we're assuming that the order in the top 10 does matter. Right? The first order or the first song is considered the best and so on. You could just simply change it. How many different playlists of 10 songs could you come up with if order does matter? As simple as that, just showing that there needs to be an order to what you're doing. Or how many different ways can I arrange 10 songs? Something like that. So the key difference between the two is permutations tend to involve more arrangement, combinations tend to choose more just choosing. So just choosing objects, not arranging them. Next, we're going to look at just some general calculations with our factorial notation or factorial formulas, just to again get used to the actual kind of reasoning behind it or how the calculations actually come up. So if we want to remember NCR, the factorial formula is n factorial divided by n minus r factorial times r factorial. So we have 10C7. So that means we have 10 total objects and we're choosing 7 of them. So this works out to 10 factorial divided by 10 minus 7 factorial times 7 factorial. So 10 factorial over 3 factorial times 7 factorial. And this works out to 120. So again, the idea is just plugging in, or at least recognizing what your n and your r is, and then plugging that into the formula. For B, 25C20, or 25 objects, choosing 20 of them, we have n and r. So we have 25 factorial divided by 25 minus 20 factorial times 20 factorial. 25 factorial over 5 factorial times 20 factorial, which works out to 53,130. We're going to look at two other examples. So two different formats of writing it. Again, remember when it's in kind of this matrix notation, the top number is our n, the bottom number is our r, and for D, we could write this as 8C5, and even for C, we could write 8C3. So I'm going to let you try these on your own. I recommend you pause the video to try these on your own, and then we'll come back with our final answers. So coming back to this, we should see now that for both of them, we get 56. And there's nothing wrong with this. There's no, you might have thought, well, how do I get the same answer? And the idea is that when you're dealing with combinations, there's a certain amount, or there's kind of mirrored amounts that you could get depending on what you're choosing or how many objects you're choosing. And we're going to look at this later on. We'll look at this connection to other things later on. But for right now, the main thing is just understanding how you can use the factorial notation or formula to figure out how many different combinations there are. If you do want to kind of see that little connection, again, the main thing between these is that one is 5 and one is 3. So both of these objects, or both of these kind of the number of chosen objects add up to how many in total I have. So you could do the same thing with 6 and 2, 7 and 1. So like 8 choose 1 would be the same as 8 choose 7. 8 choose 6 would be the same as 8 choose 2. 8 choose 4, well, it would be the same thing as 8 choose 4. It would be the same thing. So there is that connection there, but we'll look at that further in some lessons in the future. Moving on to some word problems to kind of use this in some context. So in English, you must read 5 novels selected from a list of 8. How many choices do you have? So the key thing here is choices. We're not trying to come up with how many lists of 5 novels we could create. We're not trying to arrange the 5 novels. I just want to know how many different options do you have. Right? You don't have to. You're not being told how to read them or in what order. So you just want to know how many different combinations do you have. Well, again, we have 5 novels that we're selecting from a list of 8. So basically I have 8 total objects and I'm choosing 5 of them. I could also rewrite this as 8, 5 as in the matrix, or C and then 8, 5. Either way you try to decide to do this, you can use your calculator. You don't, in these types of questions, you don't have to actually show the full factorial formula or notation, unless of course the question asks you to, but in most cases they won't. So 8 choose 5, and we get 56 choices. So we get 56 different choices of 5 novels from a list of 8. Example 3. In how many ways can a team of 6 volleyball players be chosen from a roster of 11? So again, the key word here we see is chosen. We're looking to choose or create a team of 6 players from a roster of 11. So we've kind of already done something similar with this, or we've looked at a question similar in one of those permutations or combinations. But in this case, I have 11 objects or 11 players. I'm choosing 6 of them, so 11C6. Or I could write this as 11.6 or C and then 11, 6. So again, all different ways that are fine. And this I have 462 ways. So again, you can always use your calculator. I believe the main one will be the NCR button that you can find on your calculator. Similar to that permutation one that you would have used in the last lessons, or when we talked about permutations. Example 4. There are 12 students on the volleyball team for boys and 10 for girls. In how many ways can a co-ed team of 5 girls and 5 boys and 5 girls be chosen. So there's a couple things to think about in this question. One, we're dealing with 5 boys and 5 girls. Secondly, it's talking about and. So and we should think of multiplying. And thirdly, we're talking about choosing individuals. So in this case, we're talking about combinations. So a lot of different things to take into account or to think about. So again, we're involving everything that we've kind of looked at in the past that we kind of have to reconsider or keep in mind as well for these types of questions. So we have to think about, okay, well, how many boys can I choose? Well, I'm choosing 5 of them, and I have, we go back and highlight it, 12 that are on the boys and 10 girls to choose from. So we're going to do 12 choose 5 for the boys, and we're going to multiply that by 10 choose 5 for girls. Or again, different ways you can write it. 12 5 times 10 5. Either way you decide to write it, we have 199,584 different combinations. Right, so again, we do have to think about, again, those kind of keywords and or that we kind of look for. And again, just making sure that we're dealing with choosing or combinations and not arrangements. For example 5, there are 8 girls and 6 boys on student council. How many ways can 4 students be chosen to attend a conference if at least 1 boy and 1 girl must be included? So again, a lot of different things to think about in this type of question. First, 8 girls, 6 boys in total. We're looking how many ways can 4 students be chosen. So again, that's telling us, or should be telling us combinations. And then the kind of restriction, at least 1 boy and 1 girl must be included. So that means it can't be all boys and it can't be all girls. So in this type of question, there are multiple scenarios that we have to think about. And there's 2 different ways we can do this, similar to what we've looked at before in other types of questions. So we have a direct way and we have an indirect way. Let's start with the direct way. If I think about these scenarios, because it's talking about at least 1 boy and 1 girl, in this case, case 1, I have 3 boys, 1 girl. Case 2, 2 boys, 2 girls. And case 3, 1 boy and 3 girls. So those are the different scenarios that I could have, right? Under the restriction that there's at least 1 boy and 1 girl and 4 students are being chosen. So in this case then, for 3 boys, I have 6 boys choosing 3 of them, multiplied by 8 girls choosing 1 of them. And again, the reason that I'm doing this where I'm multiplying and here is telling me to multiply. So 6 choose 3 times 8 choose 1 is 160. For the second case, 6 boys choosing 2 multiplied by 8 girls choosing 2. Works out to 420. And for my last case, 6 boys choosing 1 times 8 girls choosing 3 works out to 336 different ways. Now, because the scenario or the question is asking at least 1 boy and girl, all 3 of these scenarios are valid. So it could be case 1, case 2, or case 3, And when we have that, we can think of or. We've seen situations like this before. So when it's or, we are adding all of these up. And we get 916 ways. So 916 ways forged students can be chosen to attend if at least one boy and one girl must be included. If I were to do this the indirect way, I would need to do the total ways minus the complement to my situation. So the opposite, or the complement of at least one boy and one girl, is one scenario where there are no boys and minusing one scenario where there are no girls. So no boys means, all girls, and no girls means all boys. Just to help us keep that in mind when we're going through and doing the calculations. And when I find this out, this would work out to at least one boy and one girl. So the total number of ways minus how many ways I can choose for students with no boys and how many ways I can choose students with no girls would work out to how many ways with at least one boy and one girl. So if I go through this situation then, how many total ways can I choose for students? Well, I have 14 total options, choosing 4 of them, minus no boys, or how many ways I can choose with no boys. So 6 boys, choosing 0 of them, multiplied by 8 girls, choosing 4 of them, minus, for the second part, for no girls, 6 boys, choosing 4 of them, multiplied by 8 girls, choosing 0 of them. So again, the and is in there because it's no boys or 0 boys and 4 girls, 4 boys and 0 girls. In the end, it doesn't really make a difference because 8 choose 0 is 1 anyways, or 6 choose 0 is 1. There's only one way you can choose none of them. So in the end, it doesn't really matter, but you do kind of want to keep that habit there of including every part of it. So when I go through and calculate this, I should find there are 1,001 ways, or total ways, minus 70 ways for all girls, minus 15 ways for all boys, and in the end I get 916 ways. So regardless of how I look at this, whether it's direct or indirect, I should still end up with the same answer. In example 6, we're going to go back to that Lotto 649 kind of question or warm-up that we did and answer some questions based on that. But before we do that, today's code word is charge. Again, today's code word is charge. So coming back to this question, in Lotto 649, 6 numbers are chosen at random from 1 to 49. And we talked about, or in the beginning, we talked about there is no order to these numbers. It doesn't matter what order your number's in, the idea is that you're picking the right 6 numbers. So how many ways could you choose your number? Well, I have 49 total numbers to pick from, and I'm choosing 6 of them. I have to choose 6, so 49 choose 6 equals 13,983,816 ways. So again, tying this back into the warm-up, this is a lot more manageable and a lot more realistic. In the entire province, you could sell 13 million lottery tickets. And there's definitely a chance that someone is going to choose the right numbers. B, to win a second place prize, you must match 5 of 6 numbers. How many second place prizes are possible? So here we have to think of it in 2 parts. because the main thing is here, we must match 5 of 6 numbers. So that means in our scenario, 6 or 5 of the numbers must be correct. And out of all my options, there are 6 correct numbers, right? In terms of winning numbers, there are 6 correct ones. I don't know what they are, but I just know that there are 6 of them. So 6 choosing 5, and this is going to be for the number of winning numbers. So 6 choosing 5, multiplied then by 43 losing numbers, choosing 1, because one of my numbers is incorrect. So 43 choose 1 is the number of losing numbers. And I get 258. So there are 258 ways that I could match, or 250 combinations that I could match, or where I could match 5 of 6 numbers. So again, I have to think of matching 5 of 6 numbers, and I can also think of and one that doesn't. So 5 numbers match, 1 number doesn't. So that gets me my calculation. 258 ways. What is the probability of winning 3 numbers? So we'll touch on probability a bit now, and we'll come back and look at it later. But again, remember, probability is equal to NA over NS. So we're going to separate it into 2 parts. How many total ways, or how many total combinations, and how many winning ways. So in this case, NS we've already done. 49, choose 6, which gets me the 13,983,816 ways. So that's my total number of combos or combinations. For the number of successful ways, or the number of ways of winning 3 numbers, similar to the last part. So there are 6 winning numbers. I am choosing 3 of them, multiplied by 43 losing numbers, choosing 3 of them. Right, so this is losing numbers. These are my winning numbers. And this works out to 246,820. So putting that all together, probability is going to equal 246,820 over 13,983,816. And when I solve this, 0.01765 or 1.765%. So it's very unlikely that I'm going to win three numbers, or correctly guess 3 numbers in the Lotto 649. So again, the main things that you should have gotten from this lesson is 1, understanding the difference between a permutation and a combination, and then 2, just understanding how to solve questions involving combinations, realizing that you're going to have to rely on some of the concepts that we've learned in previous lessons and apply it to these. So again, if you have to, please go back and review the older lessons to kind of refresh on some of these concepts, specifically with kind of the ideas of and or when you're looking at different scenarios.